is Diophantine approximation with prime restriction in number fields. And the question actually starts from the Dirichlet's problem, that is, if alpha is a real number, then for every x from natural number there exists a pair, a co-prime pair, where this a and q belongs to z2 and q is greater than 0, less than equal to x, and this modulus alpha minus a divided by q is less than equal to 1 by q of x. So as a consequence, we will get that if alpha be an irrational real number, then there exists infinitely many pairs aq belongs to z square, such that q greater than 0 and GCD of a and q equal to 1, and this modulus alpha minus a by q is less than equal to 1 by q square, and this can be explicitly produced by continued fractions. So if I now restrict the denominator here, this q, by primes, then this is an interesting question. So basic question is that let x naught be an irrational real number, so for which nu greater than 0 can you prove that there exist infinitely many primes pi such that modulus of x naught minus p by pi less than equal to pi to the power minus 1 minus nu plus epsilon for every epsilon greater than 0. So there are some results in that direction. So we expectation is nu equal to 1, and we can prove under GRH that nu equal to 1 by 3, and there are some results in that direction. So first is Vinogradov in 30s who proved that nu can be 1 by 5, then 1 by 4th by Vaughan is 1978 by using Vaughan's identity and the refinement of Fourier analysis argument, and 3 by 10 is Hermann, he introduced his sieve 1983, Hermann sieve, and then 4 by 13 Gia 1993, 7 by 22 again Hermann, he refined his argument, previous argument, and got 7 by 22, and 9 by 28 Gia again, and 16 by 49 was Heath Brown, and 1 by 3 is Mathemaki 2009 is averages of Klusterman sums, and this result is considered the limit of the modern technology. Okay. So what about the real quadratic number field case? However, I missed 2 points here, that is in the case of Qi, that is for the Gaussian integers, Gaussian primes, we can do this kind of results. There are results by Stefan Bayer who proved nu can be 1 by 12, and after that Hermann actually proved the full analog of his 7 by 22 results, which is in the case of Gaussian primes. But what is the problem is that he need to then sum the trigonometrical sums over complex numbers. I mean there are some figures actually, so it is a sharp cutoff, so there is a problem because he didn't use the smoothing. After that Stefan Bayer and Mark Technow, they introduced the smooth technique and got this 1 by 4th result of Vaughan is analogous to that, and we actually follow their path. But the problem is that if we take the real quadratic number field, due to having infinite number of units, we can't mimic the exact way what they did in the case of Qi. So first of all, we need something which is same as Dirichlet's approximation in the case of number field. So that is provided by QMA, and for corollary, I mean he proved a more general theorem, but for a corollary we can say that there exists a constant c greater than 0 with the following property. So if we take, so we have real quadratic number field, so we have 2 embeddings, sigma 1 and sigma 2. This sigma k here is exactly the ordered pair sigma 1 k comma sigma 2 k, where k belongs to this capital K. Okay, so x1 x2 belongs to R2 minus of sigma k. Then there are infinitely many principal ideals, q non-zero principal ideals, such that modulus of xi minus sigma ip divided by sigma iq is less than equal to c divided by norm of that ideal q for I equal to 1 and 2 for some generator q of this curly q, and p belongs to the ring of integers of that. So from that actually, so this QMS result we need 2 ways. First of all, it says that okay, we can ask the same type of questions in the number field, and secondly, when we proceed by calculation, we have seen, because also we have Dirichlet's approximation theorems available for simultaneous, but that doesn't give us the optimal result. So we use this one, but for that, for the latter calculation, we need some Diophantine properties of the pair. that is called good and bad pair. So if I write longhand, say suppose p equal to u plus v square root of d and q equal to f plus g square root of d, then this actually formula comes like that way. So we are demanding not only that, we are demanding that, so suppose we take this quadratic number field of class number 1 and eta greater than 0, and say suppose that x1 x2 belongs to R2 minus sigma k, is a eta good if there is a infinite sequence of natural numbers w such that this one holds, and moreover the GCD of this f and g is bounded some w to the power eta, okay, and we call this number eta good, and if it's good then it is good, I mean we call this is good if it's eta good for every eta greater than 0. Okay. One can construct however these good pairs explicitly by continued fractions, and we also showed in that paper that almost all pairs are good, but unfortunately in the latter works we have seen that this is actually not needed. But however in our paper we actually did that. So the main theorem is that if you assume that q square root of d has class number 1, where d is a positive square free integer satisfying d congruent to 3 mod 4, let epsilon be any positive real number, and suppose further that x1 x2 belongs to R2 minus sigma k is a eta good in the above sense what we have discussed. If we set nu equal to 1 by 8 minus eta divided by 1 plus 2 eta, then there exists infinitely many non-zero prime ideals in the ring of O of integers of q square root of d, such that this modulus of xi minus sigma I p divided by sigma q less than equal to norm p to the power minus half minus nu plus epsilon for I equal to 1 and 2. For and q is some generator for p, okay, and p belong this small p belongs to the O. This, okay. So if the corollary is that if x1 x2 is good, then above holds with nu equal to 1 by 8. Okay. So ultimately actually smoothing the Diophantine approximation problem here. Let me just, okay. So here we need to produce something which is actually smoothing the condition of that, this xi minus of that, if I take a summation of 1 with some condition characteristic function, so we need to smooth out it. So exactly here we did that, we smoothing our Diophantine problem. So this kind of functions fits well in the case of smoothing. I am not going to in details of this kind of function, this is the Gaussian also, and instead of because in the real quadratic number field as we have infinite number of units, so it is a very obvious way to switch to ideals. So hence our weight functions are defined on the ideals, not on the elements of this q square root of d, rather the ideals of O. So this omega q, the small omega, this omega of q, this on ideals, there is a delta square by divided by 2 square root of d dot psi q, and omega tilde q is equal to psi tilde q dot f q, and psi tilde q n divided by q of psi q, where this psi q is actually this function, and also this f q is actually f of q, this function is summation, this p runs over all the integer, all the ring of integers element, and this omega, so omega is basically Gaussian. So you can understand basically, so we if there is an exponential decay, so if it go beyond or something, this particular function gives nothing, it is a very negligible something. That's why we are actually smoothing the condition, this condition, this this condition xi modulo that one. So if we do that, then our basic goal is to derive a lower bound of this quantity t tilde n, where this is sum at omega tilde p, where p runs over all non-zero prime ideals. So if we able to get a lower bound for this, then we are done, and obviously the sum, I mean okay. So how to do that is that, so t tilde n actually measures up to units the number of prime elements q belongs to O with norm of size about n, such that modulus of xi minus sigma I p divided by sigma I q is not much larger than delta divided by square root of n for I equal to 1 and 2, and a suitable p belongs to O, right. So our approach is here how to get a lower bound for this quantity. Here we followed the Hermann's philosophy. That means, so we want to get an information for an unknown set but from a known set. We compare this set with this t tilde curly Tn, that is omega p, and this also runs over all prime ideals, non-zero prime ideals, but this I know basically. This is basically smoothing of number of primes kind of thing. The quantity Tn measures up to units the number of prime elements Q belongs to O with norm of size above 10 scaled by a factor delta square by 2 square root of d. And if it is so, the Landau's prime ideal theorem suggests that we have a lower bound, and somehow if we know that this difference is smaller than with respect to that one in the right hand side, then we can comment about T tilde n. Okay, in suitable, if the distance is not small compared to delta square n divided by log n, then we can comment about the lower bound of T tilde n. Now, how to get a difference? How to get an information about T tilde n minus Tn? So here, what we did, that is we relate this difference to the difference of shifted sums, and shifted sums comes from the Hermann sieve. So actually, we modify this Hermann sieve to the ideals. These are all technical details, but what I would like to focus on is that there are two sums, type 1 sum and type 2 sums. It precisely looks like that one, it is a weighted sum like that. If this modulus is less than or equal to y with some fixed quantity, then we can comment about the difference of shifted sums. Exactly in that case, kappa we will take for our purpose kappa equal to half, because then we can get the primes. So, and also this Tn, we can show that Tn is equal to S omega x to the power kappa, this shifted sum, plus big O of x to the power half log x, and T tilde n equal to S omega tilde x to the power kappa plus big O of x to the power half log x. So, if I have information about the difference on the shifted sums, we have informations about the Tn minus T tilde n, and exactly that we have done. So, this is the theorem. So, assuming that x1 x2 belongs to R2 minus sigma k is eta good, where eta greater than 0. Suppose epsilon less than or equal to 1 by 14, then there exist infinitely many natural numbers n such that this difference happens like that. This difference happens, and hence this T tilde n is greater than, I mean there is some constant. This constant depends on only the number fields, and delta square dot n by log n, provided that 1 greater than or equal to delta greater than or equal to n to the power minus nu plus 15 epsilon, where nu equal to 1 by 8 minus eta divided by 1 plus 2 eta, and if x1 x2 is good, then we can choose nu equal to 1 by 8. So, ultimately we are in a case of smoothing. So, if you unsmooth this one due to the behavior of the due to have the behavior of this weight functions, we can see we can cut off this one in a suitable range, and ultimately we are getting this one, which is exactly we would like to prove. So, there are infinitely many primes meaning this, and later we actually work with Stephen Bayer and Mark Technow. So, we do the better bound. It's an analog of Hermann 7 by 22, is 7 by 44 in this case, and in that case we developed Hermann sieve for ideals in any number fields, and we also provided a Hermann's lower bound sieve, and in our weight functions what we have chosen, it's somehow a relation between Hecke characters with their weight functions, and ultimately we proved the result. These are the references, and thank you.
Any questions or comments?
So, your P by Q was just a generator. So, P is a generator and Q is a generator of the
Yeah, Q is the generator of the ideals basically.
That's why you need the PID.
Exactly, because if I don't have the PID, the main problem is, first of all, we cannot talk about the GCD anyway. Though we can talk about the GCD for the ideals, but I have a doubt that in the latter case of calculations how to proceed.